Assalamualaikum students, welcome to electronics. I'm Madam Rosmina Zwin Abdurrahim. Okay, I would like to share one hadith with you. It was reported by Abu Darda radiallahu anhu. The messenger of Allah sallallahu alaihi wasallam said, "Verily the angels lower their wings for the seeker of knowledge. The inhabitants of the heavens and earth, even the fish in the depths of the water, seek forgiveness for the scholar." So I'm sharing this hadith with you again to remind you that you are so special in the eyes of Allah. Every single creations in the world, wherever you go, whatever you do, are now praying for you, seeking forgiveness for you. So again, the key is please be grateful of being students. Now we come to chapter 8, Ideal OPAMP and OPAMP Circuits. In this chapter, there are three topics that we are going to cover. The first one is OPAMP symbol and characteristics. The second one is the OPAMP circuits. And the third one are the examples related to this chapter. Okay, for the first topic, which is on OPAMP symbol and characteristics, what you have to know is OPAMP symbol has three terminals. Two terminals are at the input side and one terminal at the output side. At the input side, the terminals are inverting, the negative sign here, and the second one is non-inverting, which is represented by the positive sign here. And obviously at the output side we have the output terminal. And for OPAMP, what you need to know is you can imagine this OPAMP as having the same black box as our amplifier model before this. Okay, you don't have to know what's inside it, but at the outside of it we have two input terminals and one output terminal. And you need to take note about open loop mode, okay, where V0 is equal to AOD times V2 minus V1, where AOD is actually refers to open loop gain, which I will explain more in next slide. For OPAMP, there are two main characteristics that you need to know. Okay, this is important. And the first one is AOD should equal to infinity. Okay, so as you can see from this equation, okay, you are going to get AOD equals to infinity when V2 equals to V1. Okay, so that's why the first characteristic V2 it should always be equal to V1. Why? Because AOD always infinity. Then the second characteristic that you should take note is Rin always infinity. So remember in amplifier model, at the input terminal there is Rin, right? But in this case Rin is infinity. It's like having open circuit here. So that's why in this case no current should be going into the OPAMP. Okay, so I repeat, two main characteristics of OPAMP that you should take note. V2 should always be equal to V1, as well as no current should be going into the OPAMP. Now we come to the second topic of OPAMP circuits. And there are about 4 to 5 types of OPAMP that you need to know. The first one is inverting OPAMP. Okay, and the second one is non-inverting OPAMP. Okay, then third one is summing OPAMP. And the fourth one is differentiator as well as integrator. Okay, so for the fourth one here, actually you don't have to know into very details. Our focus will be more on the first three topics here. Okay, now we come to the first circuit, which is on inverting OPAMP. Okay, so as you can see here, remember the OPAMP symbol where it has the two terminals, inverting and non-inverting, and the third terminal is the output terminal. Okay, so for inverting OPAMP, as you can see here, at the inverting terminal, you know inverting terminal is the one with the negative sign here, right? At the inverting terminal, there is a signal, a voltage is connected to it. Okay, at inverting terminal there is a voltage connected to it, and in series to the voltage is R1, and at the feedback there is R2, the feedback resistor, and at the positive terminal it is grounded. Okay, so how are you going to analyze this OPAMP circuit? Remember the two main characteristics we have discussed before. Okay, V1 should always be equal to V2, alright, and another one is no current should be going into the OPAMP. Okay, so V1 should always be equal to V2, right? So when you understand this, you know that 1 is here and the 2 is here, right? Okay, so as you can see here at node 2, terminal 2, it is grounded. Okay, it is grounded, meaning the voltage here is 0. So if you understand V1 equals to V2, we also know that automatically at node 1 here also the voltage is 0. It's like you are having virtual ground here. It's not really there, but since we have this V1 equals to V2, so whenever node 2 is connected to the ground, automatically it is as if node 1 is also connected to ground. Okay, then another thing that you need to know is, remember, no current should be going into the op-amp. So when we have the voltage here, obviously there will be current, right? Okay, but strictly no current should be going into the op-amp. What does it mean? It means that I1 should always be equal to I2. Okay, why? Because I in is 0. No current should be going into the op-amp. So I1 should always be equal to I2. Okay, whatever input coming from, whatever current coming from the input side, it will go through the feedback resistor. Okay, so here in this case, I1 is actually V1 minus 0 divided by R1. Okay, then I2 is actually the potential difference between the resistors, so 0 minus V0 divided by R2, right? So if you rearrange this, you are going to get this V0 over V1. Okay, V1 is the input voltage, okay, equals negative R2 over R1. Okay, then in this inverting op-amp circuit, we can say that the voltage gain V1 V0 over Vi or V1, okay, equals to negative R2 over R1. Okay, then the input resistance in this case is given by R1, and output resistance in this case is given by R2. Here is one quick example related to inverting op-amp. The question is asking for the gain actually. So if you understand the concept just now, in inverting op-amp, gain is given by negative R2 over R1. Okay, so that's why you have negative 150 over 12, so it gives us the gain negative 12.5. Here is another example. But now we have additional thing here, which is a voltage source Vs with source resistance as Rs equals 1.5 kilo ohm. Okay, so this is the one. Then in this case, you have to calculate for the voltage gain. Later, you have to determine for the output voltage. Okay, so it's the same concept where you have to know the two main characteristics. V1 equals V2, right? So as you know here, it is grounded, voltage is 0, so automatically you know here also 0. Then another thing is, whatever current will be flowing here at the input, okay, let's say I1, it will be the same current going to the output, okay, because there is no current going into the op-amp. So in this case, let's say I1 equals to I2, right? Then the rest you solve accordingly, because in this case for I1 we know that it is Vs minus 0 divided by Rs plus R1, since we are having two resistors in series, right? Then for I2 is 0 minus V0 divided by R2. Okay, so if you solve for this, you are going to get AV, okay, which is V0 over Vs, okay, equals to negative R2 over Rs plus R1. Okay, where R2 is 15, then Rs is 1.5 plus 1, which is 2.5, right? Okay, so if you solve for this, you are going to get AV equals negative 6. Okay, then the question is asking For part B, you have to determine the output voltage if Vs is for 45 millivolt. So obviously you know how to solve for it, where you just substitute, okay, this V naught over Vs is the AV, right? Okay, so in order for us to get V naught, okay, so AV is -6, we times with 45 milliwatt. Okay, you are going to get the output voltage value. Now we come to the second type of op-amp circuit, which is the non-inverting op-amp. Okay, so as the name it is the opposite from the inverting op-amp. So as you can see here, now the input voltage is being connected at non-inverting terminal. Okay, so the input voltage is at non-inverting terminal, but the resistors are still at the inverting terminal loop. Okay, so we have R1 and we have R2. Okay, but the same two main characteristics remain, where V1 should always be equal to V2. So in this case, as you can see here, V2 is actually equals to Vi, right? Because at node 2 here, as the non-inverting terminal, it is connected to Vi. So what can we say here actually? Since we have Vi here, automatically at this node 1 also, it is equal to Vi. Why? Because V1 should always be equal to V2. Remember? Okay. Then the second main characteristics is I1 should always be equal to I2 because no current going into the op-amp, remember? Okay, so for I1 equals to I2, okay, then in this case you just find for the potential difference over the resistor, right? So 0 minus Vi, okay, divided by R1, okay, this is I1, and I2 is Vi minus V0 divided by R2. Okay, so in order for you to find for the voltage gain, okay, you solve accordingly. In the end, you are going to get V0 over Vi, which is the voltage gain, equals to R2 times 1 over R2 plus 1 over R1, or it might be in this form. It's just the same actually, right? AV is V0 over Vi, where it is equals to 1 plus R2 over R1. There is one op-amp circuit that I need to share with you guys here. Okay, it is called voltage follower or buffer amplifier. It's just a simple circuit where there is no resistors at all. In this case, the input voltage is directly connected at the non-inverting terminal. Okay, so as a result, whatever input or voltage is connected to the non-inverting terminal, it will be the same input or voltage at the output side, where we can say V0 equals to V1. Okay, then obviously in this case the gain is 1. Okay, so you might be wondering why we need for this buffer amplifier, because the gain is 1, meaning it does not amplify the signal, right? Okay, so I give you the scenario here. Let's say you have this circuit, okay, where the current will be flowing from the voltage source, it goes through the resistance, right? Okay, but here normally for the load, the resistance value is very low, meaning to say, okay, when you have two parts like this, okay, remember V equals to IR, where R is small, so small voltage drop will be here, okay, across the load. So if this load is connected to any LED or diode, it somehow not enough voltage to turn on the device. Okay, so meaning to say the circuit will not work. Okay, let's see if for the same circuit, but just before the load we insert it with op-amp. Okay, so by having this we can ensure that we are going to get enough voltage at the load. Okay, that's the purpose of having this buffer amplifier. You can see this example for you to better understand the buffer amplifier. So it's about the same thing that I mentioned just now. So if you consider this load which is connected directly to the source, in this case this is the load here, right? Okay, so if you do the calculation using the voltage divider, you are going to get V0 here equals to 5 volt, okay, and current is 1 milliampere. You try to calculate later. And then if you are using a buffer amplifier, you just insert a buffer amplifier just before the load. Okay, by having this, you are actually connecting the VS, the input, directly at the non-inverting terminal. So the output here, it will be equal to 10 volt, and the current is 2 milliampere. Okay, but what I want to highlight here, by having this buffer amplifier, you can make sure higher voltage will be connected to the load, and it somehow can turn on whatever LED or the diode connected to the load. Okay, the next type is on summing amplifier. Okay, for summing, as the name it will somehow sum up the input signals, okay, that will appear at the output terminal. In this case, as you can see, there are three input signal or input voltages which are connected in parallel to each other. Okay, and there is one feedback resistor. So you still can use the two main characteristics that we consider for OPAMP. The first one, V1 should always be equal to V2, right? So since here is 0 volt, here also is 0 volt. And the second one is there won't be any current should be following into the OPAMP. So as you can see here, I1 plus I2 plus I3 should be equal to I4. Okay, because no current should be going into the OPAMP. Then for I1, you can straight away see VI1 minus 0 equal divide by R1, and for I2 is VI2 minus 0 divide by R2, and for I3 VI3 minus 0 divided by R3, which is equals to I4, which is 0 minus V0 divided by R4. Okay, so if you rearrange this equation, you are going to get this V0 minus RF times V1 times I1 plus I2 plus I3. So here is the solution for the example just now. So you just substitute all the values needed into the equation. Okay, so you are going to get in this form, right? Okay, this is the output voltage. These are the ones, the equation where you substitute all the input voltage. Okay, then as you can see, if you compare the left hand side with the right hand side, it is in about the same form. Okay, so meaning to say, if you compare, you can notice that RF over R1 is actually equals 1.25, and RF over R2 times 0.5 cos omega t is actually 2.5 cos omega t, is by comparison. Okay, so by considering this, you can straight away solve for the R1 as well as for the R2. Okay, so remember, when the question is related to design, you are supposed to find for the missing parameters, which are in this case to find for R1 and R2. Then we have integrator. As I mentioned, you don't have to know into details. We also have differentiator. Again, you don't have to know into very details. And this is the summary of what we have discussed before. Okay, we discussed the inverting, non-inverting, and actually the buffer amplifier. Remember, the gain is 1, and another one is summing amplifier. For differentiator and integrator, you have to know they are there, but you don't have to know into very details. Okay, we come to the last topic of this chapter, chapter 8, which are related to the examples, but I don't intend to discuss it here. We are going to discuss it during our online class, but you can use all these examples for you to do self-revision, then we can discuss later. So I think that's all for chapter 8. Thank you very much. Assalamualaikum.